W9, total internal reflection. The picture you can see here is of a bundle of optical fibres, so we'll see how they're relevant shortly. So we've already discussed refraction, which is where light bends at an interface between two different materials. So so far we've gone from a low refractive index to a high one, in other words from air into glass, but now we're going to consider going the other way around, so going from a high refractive index to a low one. So we're not interested in this boundary here because the light's going through at 90 degrees there, so although it will slow down it won't bend. But we are interested in this boundary here where the light is going from glass in this picture into air, and as you can see it bends away from the normal. So as the incident ray, the angle it makes with the normal gets bigger and bigger, this one gets bigger still. So eventually you get the situation where the ray that would normally come out of the back of the glass block doesn't, it travels along the edge, and that angle where that happens is called the critical angle. In the diagram you can see the symbol for it is IC. So that's a very special case, and that angle, the value of the critical angle, is different for each material. There we go, IC is the critical angle, so the C just stands for critical. Now if you carry on increasing the angle of incidence here beyond the critical angle, then instead of coming out of the back of the block in this case, it is reflected back inside the block. So the back of the block here acts as if it was a mirror, so you get complete reflection. So it comes back inside the glass, and that is called total internal reflection. So total because nothing comes out the back, reflection because it's like a mirror, and internal because it all happens inside the material. Okay, so total internal reflection. Key points about it is that the light has to be going from a high refractive index to a low. So for example, from glass or water into air. And in order to get the total reflection, you have to have the angle of incidence greater than the critical angle. You always get a little bit of reflection at a boundary like that, but it's only total when the angle is big enough. So just to remind you, high refractive index could be something like glass, low refractive index is something like air, so it's from glass to air. Except that it doesn't come out into the air, it bounces back inside. Now, when I is exactly equal to the critical angle, the R, the refracted angle, is actually 90 degrees. So 90 degrees to the normal. So if we go back to the equation as it is on the formula sheet, n1 sine theta 1 equals n2 sine theta 2, we can put some values into this. Let's call I material 1, the incident bit, that will be in the glass, and 2 is the air, so material 2. So if we put those values in, when theta 1, the ingoing angle, is equal to the critical angle, so this is equal to the critical angle, we can write that, and theta 2, which is normally the angle that of the ray coming out, is 90 degrees. So we've got sine of 90 degrees here. And of course sine of 90 degrees is actually equal to 1. So we rearrange it and put those values in. We get sine of IC equals n2 times 1, so that disappears, and the n1 goes underneath here. So we've got sine of IC is N2 over N1. Very helpfully on the formula sheet, it does remind you that the smaller number for the refractive index should be on top and the bigger one should be on the bottom, because if you get it wrong you'll end up with a value of sine I which is more than 1, and you can't have a sine that's more than 1, so your calculator will tell you you've got an error. So sine IC must be less than 1. And the other thing that's worth remembering is that if the material on the outside of the glass or water, whatever it is air, then N2 is actually 1. So that makes life even easier. Okay, so applications are, the most important one probably is fibre optics. So most telecoms these days, the signals are not carried by electricity in wires, they're carried by light through optical fibres. So signalling telecoms is the most important use of them. Your broadband and telephone lines are probably mainly fibre optic cables, not wires these days. The other application of fibre optic cables is decorations. So for example at Christmas you might have some fibre optic pretty things to brighten up the Christmas tree. Another use for a fibre optic cable is something called a fiberscope, or sometimes an endoscope, and that's where medical staff want to look inside somebody's body so they can feed a tube down inside you, and the fibre optics are split into two bundles. So there's one bundle which comes from a light source, so that bundle carries light down inside you and illuminates whatever's down there, and the other bundle, the picture goes back up those and you can see what's going on inside. The key thing about this bundle is that the fibres at this end have to be arranged in the same order, same pattern as the ones at this end, otherwise the picture would be all jumbled up. I think to some extent the fiberscope has been replaced by miniature cameras these days, so you just put the camera down inside somebody and feed back the electrical signal to convey the picture. Another use of total internal reflection is reflectors, like you have in your bicycle. Very clever things this. So the idea is that light travelling towards the reflector hits the surface here, bounces, totally internally reflects, hits this surface, bounces again, and comes straight back out. So the lights from the car behind you are reflected back and shine very brightly. The really clever thing about this is that even if the reflector isn't straight on to the headlights, if the headlight's coming in at an angle like this, as you can see that this bit here, you've still got the angle of incidence equals the angle of reflection, and it bounces again here, and again you've got the angle of incidence equals the angle of reflection. So the ray still comes out parallel to the way it went in, so you still get the reflection even at an angle. Clever. Another use is a periscope. Now you can make a periscope with mirrors here, but the trouble with mirrors is they've got a glass front and a silvered back, and you can get sort of double reflections when you're using two of them like this. So if you replace the mirrors with prisms, you can see the light goes straight in here, slows down but still goes in a straight line, totally internally reflects here as if it was a mirror, bounces down to this one, and does the same at this prism here and into your eye, and you get a nice clear image. So good periscopes are made with prisms and not mirrors. And lastly, diamonds. We mentioned in a previous lesson about the cut of a diamond. If you've got the light going into the diamond, hits the back surface, if it's at more than the critical angle, it will bounce, it will reflect internally, bounce again and come back out, so you get a really bright sparkling effect of the diamond. If the angle is not correct, some of it will sort of leak out the back and it won't look so bright and sparkly. So the cut of a diamond is really important. So you can see the shape here is this one here.